I just sorry. Yeah, keep going, Noah.
Okay. For which equation, sorry?
The question is, you see this equation writing down here, EC equal to 57,000 square root F prime C. I just want to know behind it. Should I use PSI or KSI?
I'm not sure. I would guess KSI.
Why?
I don't know. I mean, we used KSI before. I don't. Didn't we just stick with KSI?
So intuitive, right? Intuitive, right? Unfortunately, you just lost the wheel of fortune, all right, for the first round. But no big
Oh man.
Right? But the right answer is actually PSI. Okay, PSI. All right. No worries. Okay. Most of our equations, let me repeat, most of our equations use PSI. Okay. Okay. So just a hint. All right. So that's the Young's modulus. No worries. And now I want you to know that comparing a normal concrete Young's modulus of steel versus normal concrete, this is called modulus ratio. Okay. This is called modulus ratio. Modulus ratio. Okay. And this is approximately equal to 8 times. Okay, so you got to figure out steel is 8 times stiffer than the concrete. Okay, steel is 8 times stiffer than concrete. So the strain corresponding to the peak strength of concrete is about 0.002. Okay, but nobody cares, right? Who cares? We only care about the failure strain. That is 0.003. Okay, so it was never about the peak of prime we care. It's about when people fail, right? Ironically, right? No, just kidding, okay? So this number here, 0.003, you gotta remember by heart, okay? You gotta remember it by heart, okay? All right, and keep going. I want to find out the modulus of rupture. So FR, modulus of rupture, FR, and turns out that's also an equation of the compressive strength of F prime C. Compressive strength of F prime C is 7.5 times that. Okay, 7.5 times that. Okay, again, question. Lucas, Mr. Gerg.
Yeah.
Hey, how are you, buddy? Doing okay?
Yeah, I'm doing good. How you doing?
Not bad. So what kind of unit I want to use here in terms of F prime C? Is it PSI or KSI?
PSI?
PSI, right? Great. That's a correct answer. Okay. Thanks. Okay. So now you can see that these summarize the basic property for steel and concrete. Okay. So now we know steel is going to be symmetric. Symmetric. So let me put down some marker here. So symmetric means in terms of compression, tension, they have the similar behavior. Okay. The yield, strain for grade 60 is about 0.0027. Modulus of elasticity or Young's modulus is about 29,000 PSI. Okay, and for concrete, unsymmetric, not symmetric at all. Okay, failure strain epsilon Cu 8.003. Okay. Steel versus concrete roughly equal to 8 times. Okay, roughly equal to 8 times. And besides the rupture, modulus of rupture 7.5 square root F prime C. If I want to add one more, EC equal to 57,000 square root of F prime C. Unit PSI. Got it? So these are the basic design properties for steel and for concrete. Okay, for steel and concrete. So now we know how they're going to behave, concrete and steel. So what do they play? What kind of roles they play in terms of bending? So let's take a look at bending of RC beams. Okay, bending of RC beams. So if I have a beam, here, and apply a moment, okay, bending this way. Okay, apply a moment bending this way. And I want to make a cut in the middle. Okay, I want to make a cut in the middle. And then from the left-hand side, I see a bending moment here. And since this is cut, okay? What will be the moment at this cross section here? What will be the moment at this cross section here? Austin, Mr. Weiger, Austin, hello.
Yep, I'm here.
All right, hey, you're a lucky one for this question. So if I have moment on the left end, I make a cut here, okay? My question is, what will be the moment here? What's the value of it? Is it m or half m?
Probably 1/2 m.
So 1/2 m. Why?
Because it's half the distance. I don't actually know.
All righty, okay. That's a brave guess. Unfortunately, you lost the second round. It was the second round, but no worries. If you remember now, it is always going to be m, okay? Common mistakes, no surprise, okay? They have to be maintaining the equilibrium. So m left has to equal to m right, always. Okay, you got it, Austin?
Yep.
Right, no problem. Okay, so if I know this, okay? So it's gonna be bending, equilibrium, everything looks good, fine. And I'm gonna say, what kind of forces, internal forces, I'm gonna have here, right? Internal forces I'm gonna have here. So I'm gonna keep drawing, and this is my half beam again. Bending moment M. And I know on the other section I have M, bending moment to balance that. But instead, let me draw it out in terms of internal forces. I need to have compression, I need to have tension force. And of course, there's gonna be lever arm in between them, okay? So if I say the compression, it has to come from something, right? So one thing I keep saying, concrete is good for compression, steel is good for tension. So the compression should come from another Austin, Horstkamp, Mr. Horstkamp. Austin?
Yep, I'm here.
Alrighty, so where does compression come from? Concrete or steel? From
Concrete.
concrete. Lucky guess, $200 in RCD credits, okay? Thanks a lot, all right? Good answer. So the tension naturally from steel, okay? Tension naturally from steel, right? So, quick question here. I have moment, I have compression, I have a tension. For the sake of equilibrium, I need to maintain the balance, right? Equilibrium, I need to maintain the balance in x direction. X direction means this is x, okay? X direction. I need to have compression. Marshall, morning. Hello.
Yeah, how's it going?
Hey, how are you, buddy? So I have compression, tension. My question, what is the relationship? Bigger, smaller, equal? Which one you pick, sir?
Well, since the moment's going up, it's going to be higher in compression. Or actually, they're going to be equal.
Yes. Good guess. Good guess. All right. You got it. Again, $100 RCDesign currency. Okay. Congratulations. Thanks a lot. Thanks a lot. Okay. So compression equal to tension. Good answer. Now, in addition to that, moment has to equal to tension multiplied by the lever arm JD, or compression multiplied by the lever arm JD. Okay. Quick review of mechanics materials. Okay. So this is what we expect to happen for concrete. Right? So once I bend it, pure bending moment, I need to have a compression, I need to have a tension in the internal forces. And this internal force has to balance out each other, compression equal to tension. And I know the moment has to equal to the either tension multiplied by the lever arm or compression multiplied by the lever arm, isn't it? So fair and square, very easy, right? Very easy. I'm not expecting a whole lot. So let's draw it out. Right? This is just a theory on a paper. Well, what happens in the reality, right? What happens in the reality? So let's take a look. I have a concrete section, okay? And I want you to pay a close attention here, okay? Like a magic trick, right? I have specific symbols, okay? I have very specific symbol for this section, all right? For this section, okay? Just one more second, let me make some students here. Okay. So I call the width of my beam in this course. Okay. In this course, this is our one. Always in terms of width B. Okay. Always in terms of width B. Okay. And the total height. Okay. Total height of the beam from end to end is called H. It's called H. Okay. And I have two bars, for example, at the bottom here, always. Okay. And the distance between the top surface to the bars, I call it D. Okay. Distance is D. And you may wonder, it doesn't look like our regular cross section because I haven't put the stirrups there. Okay. I haven't put the stirrups there. Okay. So make sure that you understand if I have a concrete cover here, usually called CB, the height equal to D plus CB. Okay. Okay. And this, since I only have one side of the concrete section reinforced, I call it singly reinforced section. Okay, this is called singly reinforced section. Of course, later, you guessed it, we'll talk about a doubly reinforced section later. Okay? All right, so this is a section. This is a section. I want to see how the stress and strain distribution looks like for this section. So first of all, I'm going to assume a neutral axis. I'm going to draw that out like this, okay? And you will also draw it again for this course, okay? For this course, okay? If that is the neutral axis, I start out by drawing the strain distribution. Strain distribution, okay? Strain distribution. So you can see that I immediately draw a linear line here in terms of strain. Linear line here in terms of strain, okay? And that comes from a fundamental assumption of a bending of a beam. That is, Tyler, Mr. Fank.
Yeah,
Hey, morning, how are you, man?
pretty good. How are you?
Good. You were in my mechanics materials class, right?
I was.
All right, so let's do a quick review. Recall, when we're trying to learn a bending, right? Bending of the beam, there's an assumption we use, right? It's called the plane section remains, drawing in blank here. Okay, recall, if I bend the beam, okay, the section start out from a straight line, plane section, and after you bend it, it remains what?
Remains a straight line.
Right, remains plane, right? Okay, so that is where the linear distribution of the strain coming from. Thanks a lot, right? Thanks, Tyler. All right, so if I have that assumption, and that assumption holds true for our mechanics of reinforced concrete beams as well, so I'm gonna say on the top here, the concrete has to fail, all right? Which is ultimate strain epsilon Cu, okay? And I don't know what it look like for the steel, but I know that the steel have a strain as well called epsilon S. Has a strain as well called epsilon S, okay? Okay, but I also want you to know that we do want to see steel yields, okay? We do want to see steel yield. So we know that epsilon S has to be greater or equal than epsilon Y, okay? Epsilon Y, okay? Peter, Mr. Schenker.
Yeah.
Hey, what is the value for a yield strain of steel epsilon Y here for a grade 60?
Is it 0.003?
Nope, that's for concrete. Try again.
002?
07. Again, 07. Great. Okay, that's a good answer. All right, so that is linear strain distribution for the section. Okay, and I know that for concrete, I'm gonna draw the stress now. For concrete, it's not linear material, so the real stress distribution looks pretty weird. It looks like a bulge shape like this. That's in compression, okay? And this is compression, okay? And the tension of steel similar look like this, okay? And this is from steel, right? The question is, what happened to this side? There's no distribution from the tensile strength of the concrete. Why is that? Because it's cracked. So the tensile strength of the concrete is neglected. Okay, very important. Tensile strength of the concrete has been neglected. Okay, so if this is stress distribution, eventually I will see a total force from concrete here, CC or C. Well, let me use CC to differentiate. And I have a tension force from steel, okay, T. And I have a lever arm JD. So I just need to figure out how much compression the concrete take and how much the tension the steel can take and get a moment from there. And I'm done, isn't it? So that's not too bad, isn't it? That's not too bad, isn't it? But there's a problem. The problem. What problem? I'll show you, right? I'll show you. So before I realize the problem, I'm just gonna proceed. I say, let me take this, right? I like this. Stress distribution, right? I like this. So let me take this out here and I want to take a look, right? I want to find out the stress distribution. So it looks like this. Again, very weird shape. Half parabolic, half rectangular, okay? And I have a tension from here, from the steel, and that's it. But this is apparently very complicated to calculate, all right? We need fast computation. We don't have time at the job site back then, okay? So stress distribution is complicated. No time to calculate. So we have to simplify it. So we have to simplify it. Okay, and this simplification process is called assumption that Whitney stress block. Okay, great guy, Whitney stress block. Okay, and what does this Whitney stress block look like? Okay, this is what it looks like. It has a section, right? It has a section, okay, that has a reinforcement, okay, and we define the area of reinforcement AS, okay, steel, right? Area of steel, and then we call the width is called B always. The height is called H. Depth is called D. Okay, don't forget all these good attributes. Okay, we're going to use them again. Okay, and then I'm going to draw the neutral axis out like I did before. Draw the neutral axis out. Okay, this is my neutral axis. Okay, and I'm going to draw my strain distribution. My strain distribution still goes like this. It still goes like this, and this is epsilon epsilon, the failure strain of concrete, and this is the compressive zone. And let me name it C. Okay, let me name it C, compressive zone. And then this is the tensile epsilon S, and notice that epsilon S has to be what? And then epsilon Y. Wade, Mr. Compton, hello.
Yes, I'm here.
How are you, man?
Doing good.
What symbol should I put here? This is for you. What symbol should I put here? Larger, smaller, equal?
I'm guessing less than.
Less than? Second time. Are you sure? Are you sure?
No.
Okay, so you're not sure. All right. So what you want to put here? Bigger, smaller, equal? Okay.
I guess greater than or equal to.
Why do we want to do that? So that's the answer, by the way. Why do we want to do that? Because we want the steel to what? We want the steel to yield, right? We want the steel to yield, right? That's a good answer, okay? Thanks. Okay, so essentially, this is too complicated, okay? And Whitney said, let's swap, okay? So I'm gonna replace this stress distribution, the actual stress distribution, with something simpler. With something simpler. How simpler? This is how simpler. I'm gonna use brackets, so pay attention, okay? So instead of this nonlinear distribution, Whitney said, let's try a block. Okay, let's try a block. And after elaborative and rigorous calculations in the process, which you don't want to know, and the width of the block has been determined to be a 0.85 F prime C. Okay, and the height of this block is called A, and that is equal to a beta 1 is a coefficient multiplied by the actual compressive zone C. Okay, A, which is the effective compressive zone, smaller than the actual compressive zone C in the equation beta 1 C. All right, and then I also have a tensile forces, okay? Don't forget, since I want the steel to yield, remember this, and my force or my stress in the steel has to equal to Fy, okay? Yield stress, okay? So this is the Whitney stress block, okay? Whitney stress block, simplified, okay? Very important, okay? So given all these stress block, things are much easier. So if I want to calculate the total compression force from this block, okay? If I want to calculate the total compression force for this block, it's just an area of this rectangle, right? Area of this rectangle, right? Justin.
Yep.
So what will be the calculation for it? So what's the area for this red rectangular Whitney stress block here? What's the area for it?
It would be A times 0.85 F prime C.
Yes. Is that done? Is that complete?
Yes. Oh, then you'd have to subtract off the steel modulus, right?
Well, before that, are you looking at my table? Are you looking at my tablet?
Yes.
Right. So there's a width. Don't forget. Okay. This is only one slice. You need to multiply by the width. Okay.
Gotcha.
Good answer. Okay. Good answer. So that's 0.85 F prime C B A. Okay. Always remember B. Okay. I can't stress this enough. Okay. All right. Thanks a lot. And this is the total compression force from the concrete. All right. So I'm gonna pick our ladies next time for the next question. Okay. Let me try Regan.
Yeah.
Hey.
I'm here.
Okay. So question for you now. Since it's a rectangle shape, all right, and my compression force I just calculated out from Justin, and what will be the distance between the top and to the compression force?
Wouldn't it just be A over 2?
Thanks. Okay, answer. So that's the distance. And then the rest of the distance, which means the distance between the compression and the tension will be D, remember D here, minus half A. Okay, and that is our lever arm, JD here. Okay, all right. So that is essentially it. And that's the tension force. So let me write it out, okay? So Whitney stress block give us a very, very huge advantage. So the total compression of the Whitney stress block is 0.85 F prime C, okay? BA or beta 1 C. Okay, I want to write this out, okay? So 0.85 F prime C BA. Okay, now we know that the tension equal to AS, which is area of steel, multiplied by the yield strength, okay? Yield strength of the steel. In this case, if it's grade 60, it means 60 KSI, right? 75 KSI, okay? And etc. so on and so forth, okay? And don't forget, the compression from the concrete always equal to the tension from the steel, okay? Concrete equal to tension from steel, okay? So from this is the equilibrium in between. We have some derivations. We know that from this, essentially from this, okay, 0.85 F prime C, okay, BA equal to this, right, AS Fy, okay? So I can actually get the effective, this is called effective compressive zone. Effective compressive zone from this equation here, which equal to beta 1 C. Beta 1 is the reduction factor we can talk about, equal to AS Fy divided by 0.5 F prime C B. Okay. And then don't forget the actual compressive zone C equal to A divided by beta 1. Okay, A divided by beta 1. Okay. And you realize that beta 1 was introduced here earlier by Whitney. Okay, it's introduced here earlier by Whitney. Beta 1, he just introduced it. He hasn't given definition of it. So now we're going to give a definition of it. What is beta 1? What is beta 1, right? So beta 1 is a reduction factor or coefficient, okay, in Whitney stress block. Okay, the Whitney stress block. Okay, and beta 1 actually has an equation from ACI followingly. Okay, so beta 1 would equal to what? Beta 1 would equal to 0.85 when F prime C is smaller or equal than 4 KSI. Okay, and beta 1 equal to 0.85 is an equation minus 0.05 multiplied by F prime C minus 4 KSI. Okay, or beta 1 equal to 0.65 when this is when F prime C smaller than 8 KSI, bigger than 4 KSI. Okay, and 0.65 when F prime C is bigger than 8 KSI. Okay, so if I want to draw this equation out, I actually have beta 1, and this is in terms of F prime C, and this is 4 KSI, this is 8 KSI, then beta 1 should equal to a 0.5, okay, and 0.65, and in between you just have a linear interpolation. Oh my horrible linear line here. Finish that. So, okay. So this is what beta 1 looks like. This is what beta 1 looks like. So why do I care about beta 1? Because I needed to compute my actual compressive zone C here. Actual compressive zone C here. So why do I need actual compressive zone, you may ask? That is because, go back to the strain diagram. So notice strain. Okay, I have my strain diagram, looks like this. The top is concrete strain, epsilon Cu. Okay, my actual compressive zone C here is A divided by 1, don't forget, okay? And my steel is right here. Remember, we always say that epsilon S ensure epsilon S has to be greater than epsilon 1 yield strength. Why is that? Because this is prerequisite or requirement for Whitney stress block. So it means if you want to use Whitney stress block, right, the steel has to yield. The steel has to yield. Okay, the steel has to yield. So what does it mean? It means epsilon S, which is the steel here, in this triangle here, equal to a D minus C divided by C, similar triangle here, okay, multiplied by epsilon Cu, okay, and this has to be greater or equal than epsilon Y, okay, which equal to yield strength Fy divided by the Young's modulus scale, so yes, okay. So you have to check this step every time to make sure it yields. Make sure it yields, okay. So after you check this step, make sure you can use Whitney stress block, then you can find a nominal moment now. So the nominal flexure capacity or nominal pressure strength, we talk about this, Mn, okay, should equal to either tension force multiplied by JD, that is D minus half A, or compression force CC, E minus half A. Okay, now since epsilon S bigger or equal to epsilon Y, the stress in steel equal to the yield strength. So Mn, the tension equal to ASFY, so Mn equal to ASFY E minus Fa. Okay, so this is the final equation used to calculate the moment of flexure capacity of the beam. All right. All right, so this is the procedure to calculate. So let me show you an example, okay? Let me show you an example, all right? So example number 1. Okay? Example number 1. And now I have a beam, and the beam looks like this. nice rectangular beam. Nice rectangular beam. I have a width of 12 inch. That is equal to B. Height equal to 20 inch. Okay. And I have 4 number 8 rebars. Question. Here comes the question now. Be alert. All right. And my question is, I have 4 number 8 rebars. Okay. My question is, Mohammed, are you there? Mohammed, Mr. Kabandi, are you there? Mohammed, all right, he's not in. Okay, so I'm gonna switch to our next victim who hasn't done it. Oh, John, there you go, John.
Yeah, I can hear you.
All right, so quick question here. What is the size of
Yes, I'm here.
So what's the size of number 8 rebar? Let's do that. What is the size of number 8 rebar?
Are you asking me or Abdullah now?
I'm sorry?
Are you asking me or Abdullah? He came back.
I'm asking the diameter of the number 8 rebar. Okay.
Is it 8 centimeters?
Oops.
Yeah, I don't really know.
All right. So remember we said last time, the size of rebar goes by 1/8 inch increment.
Oh, yeah.
So try again. What's the number 8 again?
1 inch.
Good answer. Okay. Now remember. Okay. So that's 4 1-inch rebars at the bottom here. Okay. I have a concrete cover of 2.5 inch. All right. So I know the concrete is FRMC 4 KSI, normal strength concrete, and I'm gonna use the strength of grade 60. What's the yield strength of grade 60? Question here. Jeff, Mr. Feeler. Jeff. Hello.
Yeah. You said the yield strength?
I'm asking you for the yield strength. I'm using grade 60 here. Grade 60 here.
Is it 29,000 KSI?
Oh, that's the Young's modulus. I'm asking.
Okay. Is it 0.00207?
That's the yield strength, right?
Okay.
Third time the term. What was it? Give you a hint. 60.
I'm sorry, what?
The yield strength for grade 60 rebar is what KSI? How much?
Oh, I don't know off the top of my head.
Right, okay, it's 60 right here, isn't it? Okay.
Okay.
Right, so every time we tell you grade, right, that's the yield strength. Okay. So if I say grade 75, the yield strength is 75. Okay. Good answer. Okay. So that's the yield strength. So now this is the section I give them. Okay. What will be the nominal flexure strength MN here? Nominal flexure strength MN here. Okay. All right. So let me run with this in. I think I still have 5 more minutes. Okay. So to solve the problem, immediately I'm going through the Whitney stress block. So first, okay, always draw. I want to see the diagram every time in your homework, okay? Draw the diagram, and the diagram looks like this, okay? 1, 2, 3, 4, 4 rebars at the bottom, okay? And neutral axis right here, okay? And I draw the distribution in terms of stress, okay? Sorry, in terms of strain first, okay? In terms of strain. Okay, so on the top here is epsilon Cu, okay? And that is always 0.03, okay? So let me remove this space, more space here. Okay, bottom here, epsilon S, and I'm gonna make sure epsilon S is always bigger than epsilon Y. Okay? But then the Whitney stress block says I have a rectangle distribution compression. Okay, don't forget this is compressive zone C. Okay, and this is A, is smaller than C, beta 1C, and this is 0.85 prime C, okay? And I have a tensile stress, okay? Tensile stress here, and this is ASFY. But anyway, I'm going to use FY here. Okay, and this is distribution, okay? Distribution. Okay. All right, so that is the stress. Okay, so strain, always draw this, okay? From starts on the left section, you start from section, you draw strain, you draw stress, and then you draw internal forces. So this is CC. Right here is half a distance away from top, and this is tension T, and that is ASFY for T. CC is 5 F prime C B A. Don't forget B. Right? Okay, so essentially that is the equilibrium. That is equilibrium. So this is called internal forces. That's why I call it short forces. Okay? And let me say this. If you don't remember anything on top of your head during the exam, okay, that is you have drawn a blank, you have a fight or flight response, don't know what to do. At this point, draw this diagram. Okay? Draw this diagram. Okay, it will help you. And more importantly, if I see this diagram and if it makes sense, I will give you partial credits. Okay, let me say this again. Ooh, partial credits. Okay, very hard to come by these days. Okay, very hard to come by these days. No discount, no nothing. Okay, so once your head is drawing the blank, don't know what to do, draw this diagram. Okay, draw this diagram. Okay, I'm gonna write it here. Partial credits, guys. Sales event. Okay. Partial credits, remember? So know by heart how to draw this diagram from section, strain, stress, and forces. If you miss one, no credits, okay? If you miss one, no credits, okay? All right, this is to stop. We're gonna continue this problem. We're gonna continue this problem, okay, next lecture. So I'll see you on Wednesday, okay? All right, so feel free to stay a little bit late if you have any questions. I can stay till 10 o'clock, okay? If not, I see you for Wednesday, okay? I see you on Wednesday. All right, bye now. Thanks.
I got a quick question.